Hello. I hope this is going to work today because it's a lot of needing to look at this while also talking through what we see. So what we did today is we compared the drawing approach that you've been using, looking at percent bars for percent relationships, with a more algebraic approach. And yesterday we worked with a percent proportion equation that we're going to work with further today to see if we can generalize another equation that you can use. So the goal by the end of today is that you have two different equations that are related to each other, and you see how they're related to each other, that you could use given information that you've got in a percent problem. So we've got this problem here. It says, let me see if I can read backwards. Ms. Carter only buys clothes that were fashionable last year. I found a pair of pants that used to be $40, but they're on sale for 85% off. How much did I save? Okay, so I'm going to focus on the drawer first. So ignore the equator. Actually, we can just go this way. Just look at the drawer first. I want to figure out what was this person thinking as they went through these three drawings. First, it looks like they set up what they knew about the whole. They knew that they had 100% and that was going to match up with $40. That was the original price of the clothing. And then they looked at about 85% would be that unknown that we're trying to find. And in this case, that unknown would be how much off it is. Okay? So it's 85% off. That means that X is my part telling you how much off it's going to be. So if I were to write that down here, I would say they kind of set up. So $40 is whole, and X, the part, is at 85%. Next, we need to figure out what's going on with all of this stuff being broken up. They broke it up so that we had 5% and $2 on this side. A lot of people are starting to get pretty comfortable with saying, oh, if I want to get up to 85%, I could go 5, 10, 15, 20, etc. So I might as well break it down into 5% chunks. Well, 5 goes into 100 20 times, so I'm going to have 20 boxes here. Given that, if I did 100 divided by 20 to get 5, I would need to do 40 divided by 20 as well, and that would get me $2. So that's what I'm breaking it up by. So the drawer at this point broke into 5% to go through 85% and split $40 into 20 pieces. So this is where we consider that proportional reasoning. If I'm going to split this up into 20 pieces, I need to split this up into 20 pieces as well. So then, at that point, it looks like they just needed to go from 5% up to 85%, and I could shade that in. I could say, well, I need to get all the way up to 85%. And that's going to be 17 pieces. And if you did 5 times 17, you would end up with 85. So I'm going to need to do the same thing to my $2, and that's going to get me to $34. So they worked their way back up to 85%, and they got 85%, and part needed to be $34. So thinking about this model, it's really splitting it up, breaking it down to that small increment, and then working your way back up to whatever the percent is that you're looking for or whatever the whole is. The equator did something different. Our equator started with an equation, and this equation looks like a proportion equation because you have two equivalent fractions, and they had some percent on this side, because 85 out of 100 is 85%, and then something out of 40. Well, 40 is my whole, so X could be my part, so I could say part over whole is 85%, That was that percent equation that we talked about yesterday. So they started with the part to whole equals the percent equation. And they included the information that they knew. From here to here, though, things get interesting. So major difference is x is now by itself. That's useful if you want to solve for x, because you can figure everything out on the one side and say, well, that's what x has to be because it's equal to the quantity on the other side of the equation. So to get x by itself, currently it's being divided by 40. How can you undo that? What is the inverse operation to division by 40? Well, the inverse operation of division is multiplication. So if I multiply x times 40, then dividing by 40 times 40, it's going to cancel back out, and it's just going to be 1x. But we got to keep things balanced. So if I multiply by 40 on this side, I would need to multiply by 40 on this side as well. And it looks like that's how we ended up with multiplying by 40 on this side and x by itself on the other. So that's the crucial piece here. We got x alone by multiplying 40 on both sides. We used our inverse operations. Last, well, x is already isolated, so it's just an issue of simplifying. You could do 85 hundredths times 40 over 1, because we know that's the same as 40. And at this point, you could multiply across and do a lot of reducing, or you could think a little more strategically and look for things that you could simplify out right away. So I know that I could divide out 5, I could divide out 10 here and there. So I could say that would be 4/10. And then if I did 4 times 85 divided by 10, so now we have x equals 85/10 times 4 wholes. I'm going to end up simplifying all the way down to x equals 34. So at this point, it's trivial in that you've already done the manipulation. Now you just are simplifying by using what you know about multiplying fractions. Okay. So big differences here is that in the case of the drawer, they were thinking about how they could break things down. In the case of the equator, they were thinking about how can I use proportional relationships and then manipulate that equation. What do I know about inverse operations that I could use? So instead of dividing by 40 up here, could I multiply by 40 so that I now have x alone? Undo that. So over in our notes on the back, we had first what we know for our percent proportion equation. That would be part to whole is equal to the percent, which is always out of 100. And then looking back at the previous problem, we multiplied both sides by 40, and that was our whole. So you can multiply both sides by your whole, and that gives you a new equation now. The new equation would have the part isolated by itself, and that part is being, the percent is then being multiplied by the whole. So two different equations, they're telling you a lot of the same information. They're very closely related. The difference is that you now have something that's going to be useful if you don't know the part, because then you can just kind of plug it in and solve for the part, versus if you have a proportion, you're going to think about how could I be scaling up and down. And we'll look at that in this final example. So this final example says, I saved $15 on a shirt because it was on sale for 30% off. How much did the shirt originally cost? So if I save $15, probably was my part. That tells me that it originally cost more. So as an equator, I would say my part is equal to 15. My percent is equal to 30%. and my whole I don't know. Since I know the part and I don't know the whole, I'm going to start in the proportion equation because there's nothing where I have the whole by itself right now. So I'm going to say 15 over, we don't know, x is equal to 30 hundredths. That would be my equation at this point. Now, looking at that, a lot of people started to see something that they could do using what they knew about proportional reasoning. They said, well, I know that 15 times 2 is 30. So what times 2 would give me 100? Well, what times 2 is 100? 50 times 2 is 100. So that tells you that x has to be 50 in this case. So it's a place where the percent proportion was really handy because we already had some scaling that you were able to do. If you don't have the part, then that's when this other equation would be useful. We didn't talk about the drawing in class. I had that for students who wanted to look at that as well, but we didn't actually talk about that. You could definitely go through and see if you could use the strategies around percent bars and breaking things down to figure out what that percent would be and match it up. Would it be 50% like we had here? Okay. So for the homework, got a lot of it. You did some in class today, and you have 2 nights, so I would split it up if you can. For each of these, you have a choice. You should use strategies that make sense to you in this case. So if it looks like a percent bar is going to work for you, if you're like, I think I could break this down into 10%, 5%, something like that, do it. If looking at it, you're like, I don't know the part, then it looks like equation 2 might be efficient. No matter what you're doing, you need to think about how you can manipulate, whether it's that percent bar or how you can manipulate that equation. I should not see you just multiplying or dividing things because you need to be reasoning about how the whole, the percent, and the part are connected to each other. Okay? It's kind of crazy outside, so I'm going to go home because I don't know what's happening with the weather. But stay safe tonight, stay dry, and I will see you tomorrow.